Okay, so I'm waiting for the students to join. Then I will start. Okay, so let us start. So basically, today we will be discussing the, you can say, a recap. Okay, so what we have discussed, because before the internal exam, I'm not discussing about the new topic because few of the portions from this topic was still left out. So I want to emphasis on those topics. Okay, before we go to the next topic, because this particular topic is there in the internal exam syllabus. Hello, am I audible?
Yes, sir.
Okay. So basically, I will be just discussing a brief regarding the topic that we have started earlier. Okay, because due to some administrative work which was assigned, the regular classes could not be conducted. So since the internal exams are starting from 31st, so the syllabus, that means the chapters or the topics which you have to study for this internal, that already been circulated in the Google Classroom. Okay, so you can visit that. Now, based on that topic, a few portions need to be, once again discussed. Okay, because it need to be discussed. So that is why I'm just going through those topics which are there in the internal exam. Okay. So first of all, the topic that we have discussed, because the main portion which I have been started, or I have started discussing in this House of Optimization Technique chapter, I have started with the multi-objective function. Okay, that was already discussed. Okay, a few months ago. That multi-objective function means any particular objective, any particular optimization problem will have more than one objective functions. Okay, that means the optimization problem has to be solved based on more than one objectives. Okay, so many practical examples we have seen, okay, as well as the examples related to the engineering, specifically the electrical engineering also we have seen. Now this optimization problem means that you have to solve the problem to find the optimal solutions. That means any objective function, that is fx equals to x square plus 3x plus 4 equals to 0. So what value of x should be there that the equation should be 0? There has to be one value. Okay. But if you're having a complex equation, okay, and the order of the equation is suppose 10 to the x to the power say 100. In that equation, you cannot solve the value of x, okay, because there will be 100 solutions of x. Okay, you cannot solve those solutions, okay, in a, you can say mathematical or using a, or you can say by using your hand, okay, hand calculations, because you need to use a computer. Now what technique the computer will use, because you have to specifically write a technique, an algorithm or a program to solve those equation which of having order of 100. So x to the power 100, you cannot write any equation or solution technique like that. Okay, so that is why it has to be solved using iteration method. Okay, now iteration method means it is generally you have to find the values of x, okay, and start with some value, certain amount of value, okay, with that should be within the specified limit. And once you proceed, you will put those values in the particular function. You will see that it is satisfying the actual function equation or not. If it is not satisfying, then you have to update those variables. Okay, update the values of those variables, which are called the control variables. Now those control variables, once you update, that is x1, x2, dot 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 up to x100, 100 solutions of x. Now, after a certain time, after a certain iterations, you will see that those values have given you some solution which is satisfying the objective function. Okay, and if you keep on updating the values, you will see that the variables are not getting updated. Okay, that means there is some very small difference between the solution to the variables. That is, suppose the solution of x1 is 4.3. It is the optimal solution. So if you update it, next iteration, you will see it is still 4.3. Okay, that means you have reached the end of the optimization problem. Okay, that means it's already solved it. You have found the optimal solution. Optimal solution means the best solution which a particular technique can produce for a particular objective function. Now, from where you have to start? You have to start with a random variable. Suppose it is given that the value of x should be within 1 to 5. So you have to start with either 1 or 2 or 3 or 4 or 5 or any random variable. So this optimization technique, which uses this mechanism of starting the solution with any random variable, is called the stochastic technique or stochastic optimization. Okay. Stochastic optimization follows the method of starting with a random variable for each object of each control variable. Okay, that means you take x1 equals to 5, then x2 equals 3. That means all the x should be within 0 to 5. So x1 is 5, x2 is 3, x3 is 3.5, x4 is 4.2, x5 is 1.7, like this. You start with a random variable. Okay. Then you put the solutions and you check the comparison. So stochastic optimization methods are optimization methods that generate and use random variables. Okay. For each stochastic problem, the random variables appear in the formulation of the optimization problem itself, which involves random objective functions or random constants. So that means this particular control variables, which are actually assigned with some random variables, random solutions. Okay, so those random variables are being assigned to them, and you solve the equation. Now this constant has to be also there. That means constant means the limit, upper limit and lower limit. That means I have told you that the suppose the values of x will be from 1 to 5. So these are the constants. Okay, then there will be some many such constants. Okay, Now, stochastic methods also include methods with random iterates. Okay, random iterate means when the iteration can be random also, because you don't know that whether the solution you will get after 50 iterations or 100 iterations or 200 iterations. You don't know, because every technique has some different optimization method. Every algorithm or technique has some different way of optimizing. Some has fast optimization, some has slow optimization. Okay, it is not necessary that a algorithm or a technique, optimization technique, if it is optimizing fast, okay, or converging faster, will produce better result. It may happen that it gives you the optimal solution as far as it is capable of giving. It gives you the optimal solution after 50 iterations. Okay. Then if you continue to 100 iterations, 200 iterations, 500, 1000, whatever, it will, whatever value it has produced at the 50th iteration, it will continue to show that, because according to that particular technique, that solution which it has obtained after 50 iteration is the optimal solution. It is the best which it can produce. So in no way it can produce a better solution compared to, with respect to that, or compared to that. But another technique, suppose first one is just A and second one is B. So B technique reaches the optimal solution at 70 iterations. But it is observed that it is taken more time to find the optimal solution. But its solution is better compared to the solution obtained by the technique A. Okay. Why? Because it may happen that due to the complex nature of the problem, because the objective functions are very complex. Okay, and very difficult to solve. So different optimization techniques are being introduced. Okay, many can be algorithm computation technique, maybe particular nature inspired technique. Okay, different types of techniques are there. So you have to find out that which techniques gives you the better solutions compared to the others for any objective function. And also you should be able to converge or find the optimal solutions not taking too much time. That is also important, because it is not possible for you to wait for 500, so more than 1000 iterations, so to 3000, 5000, 7000, 10,000 iterations, and then you will see that yes, it is giving you better result. It is not possible all the time. In many critical cases and many too much complex objective functions, you may require that, because that is required. But in for normal objective optimization problems, those kind of techniques which use take too much time will not serve the purpose. Okay, and most importantly, for simple objective functions, any optimization technique which is taking too much time, obviously that means it is not able to converge, because a simple problem will not take, generally doesn't take too much time to optimize. It will take optimize within 20 to 30 iterations or maximum 50 iterations. Generally this is the trend. Okay, now some stochastic optimization methods use random iterates to solve the optimization problem, combining both meanings of stochastic optimization. Stochastic optimization methods generally generalize deterministic methods for deterministic problems. Deterministic method means it is actually determining some solution. Okay, there are two methods. One is deterministic, one is probabilistic. Probabilistic means it will produce some probable solutions but not determine the actual solution. It will produce the solution based on some probabilities. But deterministic problem means the problem which you have to determine by calculation method. Okay, you have to use the objective optimization technique, and the optimization technique will produce some, apart from the calculation, it will give you the result. Now comes the meta-heuristic optimization. So meta-heuristic optimization is actually the those category where we are using the iterations. Okay, so basically all meta-heuristic optimization techniques are generally stochastic in nature, because whenever you have some iteration, you are solving any problem, by using the iterative method. Okay, obviously you have to start with some random variables. So most of the materialistic techniques, so generally all of the heuristic optimization generally are all stochastic optimization also. So materialistic is a higher level producer or heuristic design to find, generate, or select a heuristic that may provide a sufficiently good solution to an optimization problem, especially with the incomplete or imperfect formation or limited computation capacity. So generally it is generally a technique where it will start with some solutions, okay, and then it will proceed further till we get the better solution, perfect solution for the optimization problem. So meta-heuristic sample a subset of solutions which is otherwise too large to be completely enumerated or otherwise explored. Meta-heuristic may have relatively few assumptions about the optimization problem being solved and so may be usable for a variety of problems. So see this one many meta-heuristic implement some form of stochastic optimization. So that the solution found is dependent on the set of random variables generated. So this already been discussed. Okay, I think this is the repeated one. Now then we have discussed the evolutionary computation techniques. So which are the nature inspired? You can see most of the techniques are all nature inspired. Okay, ant colony. Okay, then artificial immune systems. Okay, there are different techniques along with that. They already discussed this previously. Okay. And they can be single objective also, multi objective also. Now one technique was there which is under the evolutionary computation, but it was not actually nature inspired. It is called the simulated annealing, which we have discussed in the last classes. Okay, simulated annealing. So simulated annealing means that technique, if you can remember, I'm just repeating once again, that the technique where it is being inspired from the industry application. Now what is annealing? Annealing you should know because it generally in many conductors, okay, annealing method is used because in power system you have studied about the different type of conductors, okay, that means the ACSR conductor, okay, then the different conductor where we now used different alloys, okay, and the center ACSR that is steel reinforced. In now center we often glass material is also used or different alloys of materials are also used, okay, and trapezoidal conductor, rounded conductor are also used. Now over here, whenever you are manufacturing any alloy for any conductor, what you do, you mix two materials, two or three materials, you heat them, you mix them, and you cool them by natural process. You don't cool them simultaneously. You don't dump them into cold water. Otherwise, it will become brittle. Okay. So you cool them naturally. So that method of cooling the iron naturally is called the annealing. So the mechanism in which annealing takes place, the physical mechanism that has been adopted and it is being implemented using the simulation technique. That is why the name comes the simulated annealing. Okay, so it is a probabilistic technique for approximating the global optimum of a given function. So probabilistic means it is finding the probable solutions. Okay, not the exact or not determining the solutions, it is finding the probable solutions. That means you start with some random variable and the way you proceed is not by a simple computation technique that you're finding the best solution, worst solution, okay, that we know about PSO or ANT. Okay, it is not like that. It is a probabilistic technique, okay, where it is generally starting with some random variables. Then what it does, it uses the probable technique, okay, or you can say probabilistic technique of determining the solution or updating the solutions because it is determining the probable ways in which you can go to the next step. Okay. Okay. Specifically, it is a meta-heuristic to approximate global optimization in a large search space for an optimization problem. So obviously, it is a meta-heuristic technique. It is stochastic as well as meta-heuristic, because if you start with random variables, you have to proceed with the certain amount of, say, optimization, where you have to optimize the objective function by different iterations. Okay. It is often used when the search space is discrete. Okay. And the search space is discrete. For example, the traveling salesman problem, we have seen the traveling salesman problem, or I will also repeat once again. Okay. So let me go to this particular technique once again. Okay. Where we have just discussed basic iteration part once again. Okay. So we have already gone through this particular portion. Okay. Where we have the basic iteration part. Basic iteration part, the method actually, the pseudocode which is there, the approach is in this way, that you start with a variable. Suppose variable is s, and we want to find the optimal solution for the variable s. Okay. Now, since this particular annealing, simulated annealing is a stochastic methodistic technique, so it will start with a random solution. So suppose the initial random solution is s0. So it will assign the value of s to be s0. Okay. So now over there, okay. So now over there, the iteration technique is not like that, that it is starting from iteration 1 and then it ending at iteration 500 or 1000, not like that. We generally, uh, what we do, we start with a temperature, as if we are replicating the annealing process. Okay. Annealing means, as I have discussed, that it is the method by which any particular conductor, once it is heated, okay, or alloy is manufactured, it is casted, okay, then it is allowed to cool naturally. So by natural process, it is cooling down. So once it is cooling down slowly, so it will slowly, you can say, gain the properties of the particular alloy. So it is cooling down, and when the temperature is at normal temperature, room temperature, then the annealing process stops. Similarly, here in the simulated annealing, we also start with some temperature. Now we know that temperature falls down if you are starting with, say, 500 degrees Celsius or 1000 degrees Celsius. Then temperature will slowly fall down. Okay. So now, how will it fall down? Generally, yeah, will it fall down, say, depending upon the environment. Suppose from 1000 degrees Celsius to 999 degrees Celsius, how much time will it take? We don't know. It is based on the particular material which is being cooling down. Number one. Number two, the environment temperature, where we are doing the annealing process. That is also important. Okay. So based on the factors, the rate of falling of the temperature depends. Okay. So now we don't know, because we are replicating that particular method of temperature falling down. Okay. So we are not actually having a iron which is of molten iron melted. Okay. And we have to go for the annealing process. What we do, we take a random, say, of a higher limit, suppose based on the objective function. Okay. So we take that maximum temperature to be, say, 500 or 1000. Okay, now how will it slowly cool down? So we take a value of k, suppose k equals to 0, okay, and we take a maximum value of k max, okay. So now slowly the value of k will, or you can say, take a value of k to be 0.5 or zero point 0.1. So based on that, the temperature will fall down, okay. So it can fall down by, say, 0.05 or 0.005. So how much iteration will it take? So if you are taking 1000 temperature maximum and you are allowing it to be 0, then every interval step will be zero point 0.5, then that means it will take 2000 iterations. and every step it is 1, then it will take 1000 iterations. So based on that, we generally assign the value of k and k max. So it is starting from a higher temperature. Then what the algorithm will do, the algorithm will search for a variable which is nearer to that variable of S0. S0 is the initial one. Okay, initial one. So we are having some random solutions. Okay. Okay. So we are having some random solutions like this. Okay. We have some random values. Suppose this is 5, this is 3, this is 4, this is 2.5, okay. This is 7.1, whatever values are there. Suppose this is the best, this is the initial random variable. What we will do, if you will not, in the next iteration, if you will not take say 7.5, what we will do, it will take the variable close to it, either 2.5 or 4 or whatever surrounding it. Then it will take this value. If it is better than that, if you put the value of 2.5 and your objective function is showing better result, then you take 2.5 in the next iteration. If it is not showing, then you take 7, 1, 1 as it is. You don't have to replace it. Then after the second iteration, you again take another variable 4. If you see this is better, then you take 4. Then again you select the next variable, okay, which is closer to it. In that way, this optimization technique performs. Okay, it is constantly searching for a better solution at every step. So this was actually graphical, you can say animation was the GIF, which I have shown you in the earlier class. I'm just repeating once again. You can see the objective is to find the highest peak, okay, tallest peak. You can see the temperature starting from 25, okay, and the temperature is falling down using this step of 0.1. The temperature is falling down from 0. Using 0.1 as step. That means it is starting from 24.9 and 24.8 and 24.7 and slowly it will proceed. It is proceeding very faster and it will reach to 0. Okay. Now, initially what happens? It will start with any random value. Suppose it has started from here. Then it is seeing that yes, for me, this is the initial value. So this is the highest peak because I have not explored the entire population or explored the entire search space. Next, what it does in the next step, if it is selecting this value, then obviously this is not better. This is worse than the previous value. This is somewhat number one. This is number two. This is worst. Okay. So what it will do? It will not take this. It will stick to one. Okay. Then it will take this value. Suppose, and you will see that yes, this is higher. This is better. But is it the highest one? Because if it is selecting the fourth one over here, then again it is shorter. So you will say that you declare that yes, this is the highest one, but actually highest one is this one. That is why it will search randomly everywhere also. Okay, not only four, then again come back to here. No, you will again search here, you will search here, you will search here, and it will store the best results within it. Suppose for it, this was the best. This was the best. Okay, so it has stored in some variables, say B1, best one. Then if you go to 4, no, 4 is not better. Then it will go to here. This is not better. Here, it will continue. And it will reach here. Yes, this is then better, B2. So B2 is greater than B1, so it will reject this. Then again, it will search this space. This is also higher, but this is the highest. So if you follow this particular red line, you will see it is starting from somewhere over here. Okay, it has started from here. Then at the end process, you can see it is comparing with this point and this point to check whether actually which is the highest one. Then it has stick to here. Then after sticking to here, you can see it is constantly moving, shaking. Why? Because it is taking some time to judge whether this is the highest point or this is the highest point. Wait. this is the highest point, or this one is the highest, or this one is the highest, or this one is the highest. It is taking some time to judge exactly which point is the highest. That is why it is shaking somewhere over here, and then it is coming closer to this peak point, and then it is settling down. So that means it has reached the maximum optimal solution, which is the highest peak. Okay. So simulated aligning search for a maximum. So it is searching for a maximum. The objective here is to get to the highest point. In this example, it is not enough to use this simple hill climb algorithm, as there are many local maxima. So hill climb algorithm we will discuss in the last class. Hill climb algorithm is a outdated algorithm which is also used for finding the maximum point or minimum point. But if you use the hill climb algorithm over here, what will happen? Since initially we have started from here, so if it is reaching at this point, so it will declare that yes, this is the maximum point. But it is unable to search the entire space because it is declaring the highest point based on the analysis, initial analysis. That means this is the local maximum, not the global maximum, because this is the local maximum for this region. This is the local maximum for this region. Okay, this is the local maximum for this region, and this is the local maximum for this region. But this local maximum is actually the global maximum. So the hill climb algorithm is unable to determine the global maximum. Okay. Okay, so it is only determining the local maximum, like hill climb algorithm, but the simulated annealing can determine the global maximum. So traveling salesman problem we have discussed previously. That let me once again repeat it. Okay, that suppose there are 6 locations. Okay, A, B, C, D, E, F. Okay, and the salesman is starting from here. Now the route from A to B is this, from B to C is this road. Okay, C to D is this, E to D to E is this, E to F is this, and F to A is this. Now there are other methods also. You can move from A to C by using this line. Okay, then A to F straight line. Okay, A to E using this curved line. Okay, different paths are there. So that means the question is that salesman is started from A, and he has to travel B, C, D, E, F everywhere. So everywhere there is a delivery. It has started from A, then so which way he should proceed, whether A to B, B to C, C to D, D to E, and E to F, and again to A, or he should proceed in different ways. Suppose F, then C, then E, then D, then C, then B, then A. Why? Because he is shorter. Okay. So in which way, or whether he should proceed like this, say B, then C, then D, there is a straight line. Okay, then E, then F, then A. Okay. So because it has to take the shortest minimum route so that can save the minimum time and minimum fuel. So this technique can be solved by using the simulated annealing. So here each state is typically defined as a permutation of the cities to be visited, and neighbors of any state are set of permutations produced by swapping any two of the cities. Okay, that means whenever you are swapping any two cities, neighboring cities, is called a move. That means whether you should choose A to B, B to C, or you can choose A to C, then C to B. Okay, or for example, that is called a swapping. Okay, That is being mentioned that you are moving, or you can say you are changing the route. Okay, so which is the optimal one? It has to choose. Okay, so now it is not possible because you have to calculate that. Suppose it can be A to B, then D, then E, F, then A, or it can be A, C, D, B, F, E, and then A, whatever. So which is the better one? It will continuously switch. This is number one. So it will see that it is traveling say 15 kilometer. It is number two. Suppose it is traveling say 21 kilometer. So it is better. Then again it will change the orientation. Okay. In this way it will see that which is the better route, the shortest one in that way. Okay. This is the traveling salesman problem. Just an idea. Okay, so I'm ending my lecture today up to here. Okay, so those who have not visited or attended this, they may go to the YouTube. Okay, I will upload this, and after you finish this particular internal exam, then I will discuss two more algorithms, search technique. That is the random search is one technique, and another technique is the downhill. Okay, downhill technique also, that I will also show because that is there in the syllabus. I will discuss those.
Okay, sir.
Okay,
Thank you, sir.
okay, so thank you then.